areas. And because of that, I'm trying to keep it very general so that everyone can follow.
Is it okay if we record you?
It's okay. Yeah. So I work on this kind of random geometry side of things. In 2D, should maybe say, if not evident. And the motivation is from statistical physics, critical models that you may know are supposed to be described by conformal invariant quantum field theory. And then there are various questions you can ask how to make this precise. And one is to look at the geometric properties of those in terms of some random curves. So maybe just a very quick motivation thing to keep in mind, if this is really the first encounter for you of this kind of stuff, is Ising model. So understand critical phenomena. Yeah. So for instance, in terms of geometric features, so a canonical example, yeah, is critical Ising model in 2D. And I'm not going to define it because you can Google the definition. I'm just going to draw some stuff. So let's say in some grid approximation of domain. So let's say domain D on the Riemann sphere or on the plane, maybe bounded. So we can draw some stuff. And so you know that at criticality, for instance, correlations of spins in the spin Ising model, they have some kind of polynomial decay in the distance of the spins. So you can see some kind of self-similarity, for instance, from RG arguments or so on, or you can just simulate it and see. So now I don't have slides, but you can maybe look from the internet. So let's say we have our domain, and obviously I should actually take a discrete approximation. So let's say we often do just a square grid, and then delta is a mesh of the grid. And as delta go to 0, you somehow expect CFT. So that's somehow the mantra. But so what does it mean? Of course, you can look at the spins, see how they converge to something which would be the spin field. Try to look at other observables and prove they converge, but it's not always possible because these discrete quantities, they may be very ill-behaved, so taking limit is difficult rigorously. But one possible approach is to look at interfaces between spins. So let's say, we have spins, right? Let's say sigma x. Vertices of this graph. Maybe I should call it something. G delta, B delta. And this is takes values in plus minus 1, right? And there's some interaction, which is the Ising-Gibbs measure. So then if you draw them on your, let's imagine you have some grid. I think most of you have seen this, but just want to give you a picture to keep in mind. So at each vertex you put a spin. And you sample it randomly from the critical Ising model. So I'm talking about the ferromagnetic coupling. never mind that much. I just want you to picture it, so you don't need the details of this. So you have pluses and minuses. You can use two colors. I don't know if we have colors. Maybe.
Yes, there are many colors there.
Might be this one. So let's see. You like that? So I'm not going to color everything, but you see that then there will be clusters of spins next to each other with the same color. And then the other one. And the configuration of spins here is going to be determined if you know all the clusters, right? We can study this model in terms of clusters, or actually just boundaries of clusters, because then if you know all cluster boundaries and you know spin value somewhere, then every time you cross a cluster boundary, you flip the sign, right? So then what you will have is some kind of loops, which are supposed to live on the dual lattice, right? Etc. And, okay, something funny might happen on the boundary, right? Or paths on the grid. And let's call it G. Okay, dual grid maybe. Sorry, it's a bit messy. And then, so what do you expect? That some of these would converge to some random curves in the continuum domain. Of course, the tiny ones will disappear, right? But something will be left. And people have studied this a lot in the math literature. By the way, I will fail to cite all the important people in this talk, so my apologies already for that. I don't even attempt to do that. But so here you can actually prove something rigorously. So, even for the Ising model case, there are many other critical models for which this kind of convergence is still open. So maybe I should mention here Smirnov and his group, and also Rick Kenyon, who was looking at related models. So maybe these two people initiated the mathematical study of how to establish this convergence. Okay. So this is somehow the random curves part. And if you look at the critical point, critical temperature in the Ising model case, you expect that these random curves that survive, they have some conformal invariance properties, right? So you could try to ask, what kind of objects can there be for this, describing this limit? And if you already know a bit, for these loops, you get this so-called CLE, conformal loop ensemble type curves. And for paths, you get so-called SLE, which is Schramm-Lerner evolution. So paths would go between boundary points. I will make another picture for it. And then there's some parameter that parameterizes the universality class. So this is one example model, but you have a plethora of critical models that should have a similar kind of description. Okay. And so what I want to focus on are these paths, which is the SLE part, because then you can somehow say more easily that certain ones always survive, for example. So this is the easiest kind of setup, let's say. So if you impose some boundary condition, on the domain boundary. By the way, if you have questions, just shout because I may not see that. Okay, so you could do, say that you have pluses on one side, minuses on the other side. And inside you sample your discrete model, so here's the grid. So then the interaction of the spins next to the boundary, is kind of governed by this boundary constraint. And inside, you still see your Ising pluses and minuses. And because we are in the plane, for simplicity also in a simply connected domain, so I'm always going to draw like that. So you can explore, maybe my plus was this color, minus was that. You can explore the boundary of cluster involving, let's say, these pluses. So maybe there are some more here, and there are some minuses there, or something like that. That's actually what happens in the limit, that you will get a simple curve, which is a boundary of a cluster. Because you have more clusters inside, right? So here are also some loops. And here is a path, right? And I'm just going to forget about the loops, because it's harder to describe where they are, at least for now. But I always know that there's at least this kind of path, right? If I impose this boundary condition. And let me denote these points by something, x and y. So for instance, this is called doplution, which is just plus minus boundary condition, let's say at points x, y, which are different. So there's a cluster boundary, you can call it maybe gamma, and I could parameterize it. I'm using some parameterization that is convenient. So from, let's say, started at x, so I start exploring. I discover where my pluses and minuses are. So this is living on, G. Well, I guess, yeah. So it's actually living on the G delta, or maybe the closure. I can think about it as a subset of the domain closure. So, and then I'm going to take a limit anyway, so you can forget about this delta for the discussion here. You start from the point x, you follow, right? So then it's convenient to use so that time goes to infinity when you reach the other point, just because then it's more consistent with something else I'm going to say. Right. So I could say that this is a random path. In my domain that I've chosen. And it goes between two boundary points. It's indexed by this data. And maybe also associated to Ising model in my example. So then you could ask, can you take a limit and can you describe it?
So just to check, the x and y are really like x delta and y delta, right? They have to line.
Yeah, okay, so you need to set it up so that maybe there's some x delta, y delta, which converts to x, y, and you don't want some pathological stupid stuff happening. But this can be done. It's actually kind of a bit tedious when you look at the papers to write this convergence down, but intuitively it's really not a huge problem. Because if you take, I don't know, a rectangle or something, you can take these always points on this grid so that they don't even move. But I'm gonna think about the delta kind of not being there. So the motivation comes from the discrete model. But then I'm claiming that you can take a limit. You get a continuum object. Then you can just study that object in the continuum and forget about the model itself. But maybe just like, what's the motivation to study this object? This one initial motivation was this relation to critical models. Okay? So then for other models, I would expect the same. Other critical. And here by critical, I mean something with a second order phase transition. But we don't need it here, because what I want to do is study these objects. So don't worry if you don't know that. And now, so what do we expect? From this gamma. So it's a random curve. In other words, I should impose some probability measure or some measure on curves, you know, in my domain between the 2 points, and maybe with some other information in it. So I could say there's a probability measure on curves. And because we are at criticality, it's not hard to somehow imagine that it should be conformal invariant. Right? So I was choosing some place where I look at my Ising model. And by the way, it's important here, this is called scaling limit, that the domain stays fixed. So I'm approximating a given domain. Where did I write it? Here. So the domain stays fixed, but the mesh is getting smaller and smaller. So I have the moduli data, which is the domain, and maybe some points which encode the boundary condition. So I'm gonna get a probability measure on curves indexed by some moduli data. Of course, you can have more points. You could ask about, you know, these things on surfaces and so on, but this is not completely understood, so I'm starting from the basic case. And so what the basic case should satisfy is just that if you transform conformally to some other domain, and you keep track of the marked points, this measure on curves should transform in some conformal invariant way. So maybe I should give it a name. I don't know if all these colors are visible. So P-like property measure. It's a bit ugly, but I want to keep track of the moduli data. Actually, I'm gonna maybe call it SLE kappa. And you don't know yet what this is if you haven't heard of this before. So bear with me. Okay, so what does it mean? So if got some conformal from D to some other place, then the P in the other place at the images of the marked points. That's supposed to represent the name of the object. So this should be the push of the measure here by this map. And now if you're not mathematically minded, you don't have to worry about all this notation. It just means that if I'm sending my thing to some other place, the law of this random object just gets transformed in a very natural way. So here's a conform invariance probably. And then in particular, for me it's sufficient to understand this kind of measure in some favorite moduli data. So our favorite data will be the upper half plane with the mark points 0 and infinity, for this case of 2 points. Okay? 0 and infinity are boundary points of the upper half plane. Okay, there's a second property that I want to mention relatively quickly, because in my talks it's not going to play a huge role, but it's needed to characterize this thing, and it's natural from the easy model point of view. It's called the domain Markov property. And maybe before that, so the goal that I'm trying to convey to you in these 2 lectures is to look at this and more general measures as somehow functions of this moduli data, and relate that to some CFT correlation functions of some boundary fields. So here are some points on the boundary. It's supposed to be a boundary condition changing operator, like if you read some papers by Cardy, for instance. So this is supposed to be governed by such objects in conformal field theory. And so they are sitting in some points, and you also have your ambient domain. I guess one way to view it is also in terms of some kind of conformal blocks, but in a slightly different way than what Jörg was describing. So I'm taking this very simple-minded approach of taking some kind of concrete objects and looking how this information affects them. So if I get there, I will mention that, plus maybe some quantum group. So there's quantum group here as well. Okay, but first I just want everyone to be comfortable with this object. So, okay, domain Markov property. It's kind of, yeah.
That's a good question. So if you start having more mark points, do you allow intersections between these curves?
So in my model, no.
No.
But of course you can take other types of models. Because if you think in terms of these plus-minus clusters in the plane, they're not going to intersect, except maybe if some stupid stuff happens on the lattice level. But then in the limit, they're going to be they're going to be disjoint. And that's why, if you have more of them, you need some interaction which prevents them to intersect. But yeah, so you can play with this and construct various different objects, and some of them will intersect or merge. So for instance, Scott has worked on these interacting SLEs as flow lines for the Gaussian free field, which are something, you know, that kind of merge. So there's various things you can do. But maybe the, I don't know, relation of those things to CFT is unclear, at least to me. While the relation of what I'm going to talk about is completely clear, so I wanted to stick to that.
Maybe instead of Z2, you could just start from some lattice where you don't have those problems.
Sure. Yeah, but it's easiest to draw. So the point is that the lattice should not matter at all. I just wanted to give you the intuition. But indeed, if you take, I don't know, hexagonal lattice or something, or triangular, it's easier and you don't have any issues even in the discrete.
Do you consider any like a cusp curve, or they have like a measure 0 and they never appear? As your path, for example.
So because they don't appear, I kind of am not interested in them, I guess. Yeah. You can force something to appear, though.
So here in the conformal invariance, you sort of see it due to this boundary.
Right.
In some way. How would you understand it, let's say, on a closed surface? Because here, it seems this conformal invariance seems to be
tied to the boundary.
Yeah, you read it from the boundary somehow. Because for Ising model, there is no metric on the graph. This is something I never understood.
Yeah, so I think it's much more complicated. On a closed surface, you need to look at these CLE loops. And there, so you need to construct it some way and then prove some kind of conformal invariance or some properties. So it was constructed on the Riemann sphere. Maybe by, is it in Scott's paper? There's also Mendelin and Andregen, which is about this Möbius invariance of the CLE on Riemann sphere.
Yeah, well, you can construct CLE by just zooming in near a point. So it's like a whole plane version. So if you've constructed it, if you just zoom in near a point, then what you see locally is going to be this whole plane CLE. If you want to construct it on a torus, then it's a little bit less obvious. You know, the property you'd want to have if you condition on a loop that breaks this thing into simply connected pieces, or a pair of loops that breaks it. And conditioned on that, you have a regular CLE in that. And then if you condition on some other loops, and you want to say this property characterizes the thing somehow, well, maybe it doesn't 100%. You know, maybe because you have some issues with. You have to find the law of the total number of loops that go around. And so if you can weight by the number of loops, and you can kind of have a family of laws on the torus that are natural.
Yeah, I think it's kind of forced down to modified data there, and yet to my knowledge is not understood on surfaces completely, if I'm not mistaken.
Yeah, I mean, there's a lot of work. I mean, you guys have done some work. Colin, you've done some work on this, right? I mean, on higher genus surfaces, constructing CFTs, not specifically CLEs. I know Shin has worked on it.
Yeah.
So there's partial results in this direction, but not everything is worked out.
Yeah, because it becomes kind of more complicated. But it's a great question.
It's just that I don't have the intuition.
Yeah, you want some kind of canonical description, in some sense. So there's this conform restriction idea that I wanted to also mention, but I need to wipe down some stuff before I can get there. So just quickly, so what is this? This is some kind of exploration property. So if I explore, I start from x and I explore up to some time, so this gamma. Maybe I write and then change. So what does the measure of the curve look like after I discover some part? Conditional law of gamma after time t. So this is, let's see, I guess in my notation, p domain minus with this colored part from. I will draw it so don't break this line. So let's make some. So this is going to be displayed in my image. So here is just a slit domain, and I'm cheating a bit. I'm assuming it's a simple curve, but all I'm going to say is going to be in that region. So let's see, what is it? Given initial segment, so I'm going to start from here and I explore up to some time. And there's a natural time for the discrete, right? You just go one step at a time. For continuous, you need to fix some parameterization, but it doesn't matter much. So then here is gamma t. So what does my remainder curve look like? It's random, right? So the claim is that it's governed by the same kind of family of measures, but in the domain, d minus this slit. So somehow it's all of this remaining part, d minus slit. And then there are two marked points. So one is still this y, where I'm targeted to, but the other one has changed, because if I start exploring after time t, I have to start where I was, right? And then go on. And by this conform invariance property, I already know how to do this in other domains, right? So these two are kind of characterizing it in a way, and you can prove it rigorously. And then there's this one parameter that I was hiding. But so the idea from the Ising model is really like discovering this interface between plus and minus. And the future of the thing to be discovered is just has the same kind of distribution, right? Because here I still have pluses on this side and on this side, all the way from gamma t to y. And then on the other side, I have minuses, which I didn't, right? If you discover, how the discovery goes is that on your left you have minuses, on your right you have pluses. So then here is the same. So this is still this Dobrushin type boundary condition, right? So now the upshot is that these two properties and one parameter uniquely characterize this object.
Can I ask a question?
Sure.
So I'm a bit confused about why this is a condition, in the sense that if we look at where you started from, which is that you want to understand some boundary between the pluses and minuses,
Yeah.
isn't the curve to x and y automatically defined?
Yes, it's there, but it's random because the pluses and minuses are random,
Yeah.
right? So there's a realization of it for each configuration of pluses and minuses. But if I want to describe all of those realizations in terms of this measure, I need, to understand the measure itself.
Oh, this is really on the measure, it's not on the curve.
No, it's the measure, yes, exactly.
Right, right.
So gamma, maybe you should think about it. So gamma is kind of sampled from this measure. Yeah, so this is a measure of curve space, and you need to put some topology and so on, but I think I don't want to do all these details, so it can be done. I just want to describe the ideas to you. Happy to explain more, also privately. So then this is a random variable, right? So what I need to know is what is this measure? Yeah. And so then the upshot, which I think is reasonably natural from these ideas from some interfaces from Ising model, for example, is that those kind of properties should hold, right? And then, so there's some work to do. So this is theorem by Schramm. So there's a unique one parameter family. Such measures, let's say. Measures. What does it mean? That is satisfying this conformal invariance property and this domain Markov property. And the parameter is conventionally denoted by kappa. You can actually take it, guess, any positive number, but for us, guess I don't want to say something. So let's say it's kind of reasonably small. So in this range, this gamma is simple, injected there. Otherwise, it's gonna do something else. And there are various ways to see this parameter. I think it's very mysterious for you at the moment. So for the Ising model, you can kind of check once you do this proof. There's some computation that gives you a value of this parameter, which equals 3. But a priori, you don't know yet where it comes from, right? But it's there. And somehow I wanted to, let's see how to do it. Maybe I describe how to construct this because you see the parameter. Maybe that's the easiest way. So if you have a classification theorem, you want to kind of say that there exists such object and that is unique by these properties, uniquely characterized by these properties. So somehow, let's see. So existence. So because we have the conformal invariance, I can take my thing to be just this favorite domain. And then I can try to construct it there. And hopefully you agree that if I construct it as a parameterized curve, I know it for any time t, then I know the law of the curve. So I'm going to use this parametrization by time in this way. And it's going to start from 0, which is kind of just convenient. And okay, let's assume the simple curve region. Because then h minus this info, this is simply connected. And everything is fine. I should probably say here that this is the case of simply connected moduli. So this is related to Colin's question, what we do for other stuff, so you need to do more work, okay? And for many boundary points you can do this, so that's kind of nice. For this torus is less clear. But okay, so the simplest case, what I can do, I think about this exploration idea. So if this complement is a simply connected domain, I can find a uniformizing map from the complement to the half plane, and then it's gonna somehow collapse this curve so that, let's maybe put it here. So here's the future. So here is, I'm gonna call it GT, depends on time, right? So GT is some point on the real line. We often call it WT, just for to be specific. And now you hopefully agree that if I understand where this tip is mapped for all times, this is a conformal bijection, so I can reconstruct my curve, right? And I need to pick this in some way. And now this one is going to be evolving on R, which is the boundary of the half plane. It's called driving function. Okay.
So how do you normalize things? Because you can always translate it away, you know?
Yeah, so pick, so that, let's see, that it doesn't change the target point too much. Target point here is infinity. So I'm gonna say that, when z goes to infinity, this one is gonna go to 0. So it somehow looks like the identity at infinity. So it fixes infinity, and the derivative is also 1. And you can check this is the uniquely fitting. You can also check that there's some evolution equation for these things. So this is maybe has to be a black box. This is from 1923. By the way, that's like 1999 maybe. Something like that. So more than 100 years ago, by Loebner, who was a complex analyst. So he was studying somehow how simply connected domains in the complex plane, how they can evolve in time. And this is a time evolution of such a thing. Right? So he showed that especially in this kind of easy case, if you look at a tiny bit like how does it grow here versus there, you can find, maybe here is like plus epsilon, t plus epsilon. You can find a differential equation in time for these maps, okay? So there is the ordinary differential equation, called Loebner equation, which looks like this. It's explicit. And it involves this image of the tip because something kind of interesting happens when you approach the tip. Actually, this curve is, in our case, is very fractal. So the behavior of the function here is quite irregular. So the point is that the time derivative, gt, of our map is some explicit thing which involves this driving function. And then there's the initial condition in time. T0, t is just, sorry, z, is the identity. So this is for all z in, say, h, something like that. And it's really some computation in complex analysis. It's a little bit long if you want to do it. But the upshot is that if you know the driving function, which is this yellow function, you can solve for the conformal maps from this equation. And then you can invert them and you get your curve. So this constructs you a curve. I haven't told you yet why it satisfies these properties. Of course, it doesn't always, right? You need to make some choices. And now, conformal invariance, in particular, is scale invariance under scalings in the half plane, right? So then you want this random curve to be preserved under scalings. That's one thing. Also translations, just these points will move. So maybe it's not unreasonable to think that the W should have a certain scaling property. I write certain because I don't want to remember how it exactly goes. And this is exactly the one from your motion. So somehow you, if you know a bit of stochastic analysis, so of course the W has to be random, right? Because I want a random curve. So what kind of random W process can I put there so that these properties are satisfied? Well, something that has some correct scaling, and also that this Markov property, which is about the exploration, if you explore a little bit, the law is kind of similar. You can deduce that you have to get a Brownian motion, maybe times some speed. So I will call it square root kappa bt. So I should say maybe this arrow also involves this other property, which is about increments of W. So what are they? This Wt plus a tiny delta, let's say. So how much does it change in time? So this should be somehow independent and have the same distribution. Okay, if you don't know these words, don't worry. It's relatively basic, probability stuff. But the point is that standard Brownian motion has independent and identically distributed, maybe with time given delta. Okay, independent and stationary increments. Maybe I should say better in this way. More precisely. So the point is that these properties are only valid for version of Brownian motion if you also assume this is a continuous function. I haven't said this, but if you have a continuous curve, it's not hard to maybe believe that the W is a continuous function. So long story short, this was very sketchy, but the upshot of Schramm was that these properties imply W equals running motion times some speed, because you can always somehow multiply it by some scalar, and this is this kappa guy. And now you can concretely construct it using this method. And then you can say that we have this object that we can study. And uniqueness is just basically also following from that it must be like this with those properties. So far, so good?
Can I ask where the kappa is precisely coming from? Because if you just want the evolution of WT under conformal invariance, then that doesn't really care about kappa.
Yeah, exactly.
So it's some sort of a, it's coming from this domain Markov property.
So it's kind of like those properties only say that you have to have these independent stationary increments and some scaling property.
Yeah.
But this holds for any kappa. So for any kind of variance of the Brownian motion, normally you have the variance 1, so that the BT is a normal random variable. But you can actually scale it by some other speed. So this kind of stuff, if you make it precise, it still allows you to put some positive number here. But then I need to maybe tell you what the meaning of this is. And it's not really governed here, it's just like one parameter family. But that's the degree of freedom that you have left once you impose the two conditions. And that has to do with the universality classes, right? So for instance, what is kappa? Yep. There's one way to see it that I was hoping to describe, which is about like perturbation of the domain. Has to do with somehow the conformal anomaly. But maybe the simpler one from here is that if you look at your thing, so how does it move? So the W is moving here, right? And now it's this Brownian motion with some speed. So if the speed is really big, then it's going to move a lot, right? It's really speed. And from this side, if you invert, maybe I should do like G inverse, T, then this curve is going to kind of move a lot, right? If the speed is very, this is a conformal map, which is kind of zipping, yeah, these two sides to these two sides, and then this point is there. So it depends the winding of the curve in some sense. So yeah, it's, I guess this exploration idea really works nicely here. So the two sides of the curves are collapsed there, right? And then there's this point. So you can see that, for instance, if kappa is 0, I kind of excluded it, but it can be there. So then, when W is just, it was starting from 0, constant, and gamma is a straight line. Or, if you wish, hyperbolic geodesy. In my favorite domain. Remember that I can map to other domains by conformal maps, so it's sufficient to describe here. This is the semi-classical limit that I will not discuss much here, but I'm happy to discuss with you if you want. There are some other things. So if kappa is less than 4, it's not clear from here, but you can compute that this gamma is a simple curve. So it's looking like really what I draw. And when kappa approaches 4, the curve is almost kind of going back to itself, but it doesn't quite do that. Maybe the illustration is that. This is the speed. If you take the speed bigger than 4, then it's going to touch itself. So somehow the evolution here is fast enough so that the curve will actually come back to itself. It kind of looks like, and the boundary, also it will touch the boundary. It's making some kind of touching points in this way. And if you very courageous, you can also look at the case where the speed is bigger than 8. So these numbers come from computations using Bessel processes, but they have some meaning in physics as well. So here it becomes space filling actually. Okay. It's gonna fill everything. So there's this speed has an effect how the curve is evolving, and also it's a fractal curve. Maybe I don't write it, but you can compute Hausdorff dimension, which depends on this parameter. And Hausdorff dimension in particular, in this case of very large, the Hausdorff dimension is 2 because the curve fills everything. And in the simple curve region, the Hausdorff dimension is less than 2, right? So from the abstract nonsense, it was just a free parameter, kappa.
Wait, sorry, I missed that. So for kappa less than 8, your Hausdorff dimension is less than 2, right?
Yeah, sorry. 2. And it's some kind of explicit formula. Yeah. And here it's 1 because it's a straight line. So there are various, maybe fractal properties. Etc. that you can deduce. Maybe for physicists, just some examples, this one here. So I already said this is a semi-classical limit, kind of. You need to kind of make sense of it, right? Let's see. So if you know what is the order, here is Luther raised to under more. If you don't know what it is, never mind. Then is 8/3 the next one. So this is conjecturally, so this is a discrete model, and I'm trying to say what the corresponding CFT quantity would be. So this should be self-avoiding walk, but this is a conjecture. So self-avoiding polymers should be described by this process with this choice. Then let's see, kappa is 3. This was the Ising model. 4, we call it the Gaussian free field, or maybe you should say free boson, level lines. Then you can look at, let's see, like this one is critical percolation. This is also critical, important. Maybe everyone knows critical percolation. In the lattice, you just color, let's say, edges or vertices with the 2 colors, but completely independently, right? And then you can look at the cluster interface, and it becomes this process. Okay? Then this one would be some dense polymer. And then I think some of you work on Owen loop models. So these have some correspondence with kappa that I forgot. Should check it. So there's a plethora of things that you can somehow classify. And now you ask, how do I know these values, right?
Yeah, so physicists always go crazy when you start talking about kappa larger than 8. Because, I mean, honestly, I don't think I know what's going on there. How can you started out from an Ising model, so you want some lattice model, and then now you tell me that for any kappa larger than 8, you have something that is space filling, but already when you have dense polymers, it's completely space filling, space filling, sorry. And I don't think I can do anything more than that. So how does that work?
So there is still this kind of winding, like more and more. So if kappa goes to infinity, this thing is actually really gonna go like next to the real line and then back and like that. While the kappa is 8 is still doing some kind of exploration in a more, like in chunks. So there's some different behavior for space filling curves. So there was some paper about some vertex models. What was it? Do you remember, Scott? Maybe you were in it. Greek about
I mean,
some...
Yeah, so if you take a bipolar orientation, so if you take, on a grid, so every vertex, or every edge has an orientation. So you randomly orient the edges. And you condition on the fact that there are no directed cycles, except, and if you follow any directed path, you either end at sort of a top point where everything flows into, or a bottom point where everything flows into. So there's one source and one sink, basically. And so choose a random orientation with that property. There's just this one source and one sink. And then you can make a tree, which is the tree of, if I give you a point, you can always say, take the leftmost outgoing arrow you can. And from every point, there's going to be at least one outgoing, at least one incoming arrow. Take the leftmost. When you construct this tree, and the boundary of this tree is supposed to be SLE 12.
Okay.
So the point is there...
I would like to get the reference.
Yeah. Just look at bipolar orientation, or I can show it to you afterwards. But it's, there's also Schneider, there are a few things, but there's some very natural discrete models that are supposed to have these things as the limit.
And kappa equals 12, that's what central charge?
I can't remember, it's like -7 or something.
Okay.
I can...
-7.
So these are negative numbers for the central charges. So
Yeah, so C
So
kappa...
that's n equals -1 in the ON model or something?
Which way does it go?
yeah, we'll give you the formula.
Triplet central charge.
Plug in and see if I remembered right.
Is there a minus sign? I'm always wrong with this.
So 1/3
Something like
triplet
this.
central charge. Yes.
Okay. So, yeah.
That's magic
I
numbers.
don't know what to put here, but you can look. So there's actually some models. But so I wanted to focus on, like, not at all here or here, because I want to talk about simple curves, especially if you have many of them and you don't want them to cross. It's easiest to deal with those. But yeah, so somehow, maybe one upshot is that this is really some kind of universal or canonical curve. So you can call it SLE kappa. It's some kind of like canonical 2D conformal invariant curve. And there's still this parameter that you have that you need to fix if you look at different things. I forgot when I'm supposed to stop.
About
Okay, so then maybe just a couple of comments. So from the kappa you can also see the conformal anomaly. I think I will sketch it to you next time in the beginning. And that you can use to look at multiple curves, so more complicated moduli. And the interaction that you get from there, so this has to do with some CFT correlation functions or blocks if you wish. And you see also some quantum group if I have time. So maybe just next time. Let's see the plan so that you know what to expect. Interaction. Maybe a CFT. Interpretation, or actually Coulomb gas also. So you can write the interaction in terms of Coulomb gas. So the C kappa is going to be actually less than 1. So this is meant to be related to Liouville theory, but with the imaginary coupling constant. And okay, so if I have time, probably not. So it's going to be the same as Jörg's case. This quantum group, this is the compact one. But if you're interested, I'm happy to discuss with you, these topics more in private. Okay, I will stop. Thanks. Thank you, Harry. So, so I started already by recapping the main object that I already described to you. So the main object is this random curve indexed by some moduli data. And so far we discussed about just one curve in a simply connected domain, connecting two marked boundary points. And I was trying to convince you that this is a universal object in the sense that it's conformally invariant and has this nice Markovian domain Markov property with this exploration idea from the critical easing model. And that if you impose those properties, there's just one kind of degree of freedom left, which is this parameter kappa, which is up there. I'm going to assume kappa is not too big, so that my curves are simple, just for the sake of this discussion. I'm not losing any generality there, really, because I just want to convey how these relate to some CFT things, and those range of kappa already covers the range of central charge that I want to mention. And there was this kind of construction using conformal maps. It's a bit small, but the idea is that if you know how to keep track of the position gamma t of the curve gamma at any time instant t, you know the whole curve, right? And this was encoded into standard Brownian motion on the real line times some speed parameter kappa. And by the conform invariance property, it's sufficient to understand this upper half plane case where this was very explicit, and then elsewhere it just moved by conform map. So I hope you have some kind of touch about this object. And now, so what do I want to do? So first kind of thing would be introduce some interaction where you can actually see the relation to some CFT correlation functions. So there's always this parameter kappa that I'm kind of keeping. Often I may forget about it. So how to understand interacting curves? It's related to something called conform restriction. So that's the idea somehow. And what conform restriction means? It means perturbation of domain, kind of. Of the domain D. And you see somehow a conform anomaly there, which is related to the kappa. So if you keep in mind this easing model example, because it's maybe intuitive. So what I might want to do is to introduce, there was this boundary condition that forces the existence of a domain wall or cluster boundary between certain boundary points. So they were x and y. Now I could have maybe x1, x2, or y1, x2, y2, something like that. And have two curves, right? Or I can have 100 curves if you want. But maybe let me just do two. So now if you do your exploration in your critical easing model or some other model, favorite model that you have, you will have several of these domain walls, right? Because for topological reason, for each point where the boundary condition changes, you will have an interface or a domain wall, cluster boundary, separating the two pluses and minuses for easing or some other things. And now there's a tiny bit of more information needed, because now you see that I don't know where these are going to end up if I start exploring. So I should maybe either decide, condition on the event that they end up in this way or in another way. So in this picture there are two options, right? Because if you sample your model, you will see that these are not crossing curves. So there's more information, which is kind of intermoduli data, so it becomes more complicated. And one way to understand it is in terms of interaction of the two curves. And so what I want to start by is to freeze one of them. So maybe imagine you already explored one of them, and then how does the other one look like? So let's erase it. Explore this one. So then the other one is living on this side, so I can just like forget about this part. And I know that on this side I all have this plus in the easing model in the kind of motivating example plus spins, and here is as before. So you see that if I remove this part, it's just the same, I called it Dobrushin boundary condition, plus on all the way this side, and minus on this side. So this one just, given this exploration, becomes this kind of object. So we already understand it, right? So this is some kind of resampling type property. So maybe another idea 1 is this. Idea 2 is resampling, or exploring like one curve at a time. So if I call them gamma 1, gamma 2, so now this is gamma 2. So this says that given gamma 1, because that's how I started, the law, the distribution of gamma 2 is the law, this one is the kappa, in what? Well, D kind of, how to say, middle, which is the connected component. So if the whole thing is D, we put it here, D twiddle is this part, right? It's the part that you get when you remove the gamma 1. Maybe I could say depends on gamma 1. And then, well, I need to record the end points, so x2, y2. I hope it's very intuitive. And of course I should say that it didn't really matter that I first explore this one. So I could also first explore this one, and then the other one has the law in the remaining component.
Should the kappa be the same for both of them?
Yeah, kappa is somehow fixed once and for all. Yeah. You can try to couple different ones, but it doesn't seem to work so well. Even with the dual value, it's a bit more complicated than this. So let's keep it fixed.
What is the definition of does not work so well? What is our criteria?
Good question. So if you try, I think you can describe them for kappa and 16 over kappa, if you want, in some kind of local way using this Löwner evolution. But if you try to describe them in this way that I say, I think you need more information. So maybe it's, I should say it hasn't been done in this setup. Yeah.
But if we just consider the Eisen model and consider all possible configurations, then is it true that half of them, or approximately half of them, will be with one way of connecting, another half will be with another way of connecting, and in this sense, then there is no way to choose arbitrary different kappas for different curves?
Yeah, so if you have this underlying discrete model, yeah, of course the kappa has to be the same. But then if you forget about that, you just ask about these curves in the continuum, you could maybe try to consider different ones. But indeed, the motivation also comes from some given model, and then of course all of them should have the same kappa. The probability of different connection is maybe not always half-half, because it depends on the position of the points, right? So if these are really close together, I think this one often wants to go next to the nearest one. So there's some non-trivial information to be understood. But actually you can understand it in terms of this interaction. So it's quite nice, the story in general.
So the fact that the first walk, say, starting as an exploration from x1 might end up at y1 or y2, is that a bug or a feature?
Yeah. Yeah, I mean biplanarity. If you do a simulation.
That I understand, but now you wrote it as it ended up in y1, but it might happen sometimes that it ends up in y2, and then you would just go on and say that the next two have to go to y1.
Yeah. So I'm not able to draw both cases simultaneously, so I just pick one. So there are two ways to do it.
Yes, but
Always
are
the
they
condition
separate?
of the
They are
problem.
separate things, or it's like one thing, or it doesn't matter?
So you can. It's sufficient to do all of them separately, because then the kind of case where you don't know where they end up, this is going to be a convex combination of measures which already know the connection. There's kind of a convex set of this kind of measures of pairs of curves, maybe I should say. Like, yeah, we would have a pair, gamma 1, gamma 2 of curves, right? Random curves. And there's actually a convex set of measures for these pairs of dimension 2, kind of spanned by the two different options in a sense. Yeah, there's a lot of things that I'm not saying here. But once you know either one, I'm claiming that you can somehow figure out the rest. At least if you know the probabilities of the crossings. So it's a non-trivial problem. Yeah. And even harder if you want to change kappa for some of them. So I don't even know if it's possible to do, like in general. Okay, so how to somehow find this thing? So I told you that there's some kind of very natural property again, this idea 2. And you can actually show, like by abstract nonsense, some Markov chain argument, for instance, or some measure theory argument, that this resampling kind of property, if you decide how they connect it, it uniquely characterizes this probability measure of this pair. So it's kind of a quite strong constraint. But then by this abstract nonsense, you don't really get the construction of this thing. So maybe a nicer way is to think about how to construct a measure for this kind of pair if I already know this ingredient for one curve. Because this I get from Brownian motion, right? So I wanted to sketch some restriction property, which is kind of, if we freeze this exploration of gamma 1, then I can just say that this area that I chop off is some given piece of the domain, and then I can ask what happens in the remaining part. Now I got some notation, so maybe I should use this thing. So people talk about conformal restriction. This was maybe coined by Lawler, Schramm, Werner, around, when was it? 2000 something? 4, 3? So what is it? So if I take, so without loss of generality, I can have my domain to be the half plane, because then everything is more explicit. I'll draw a little picture here. So let's say the chopped off area is something like that. I'm gonna call it A. And then I'm gonna have one of these curves there. So you can forget about the other curve now, because I kind of imagined that I already took it. So you would take A to be some subset of D, which is now the half plane. And so that these starting and end points are not there, I guess. And maybe here my starting point will be x will be 0 and y will be infinity for the normalization. And I also want for this discussion that the complement is simply connected, like I drew here, the complement of A. If you want to do stuff, say in an annulus, then you can imagine this A is a hole. And I think the same idea works, modulo, technical trouble. So these problems have been considered in non-simply connected planar domains. but not on general surfaces. But what I'm saying, the idea should work for any kind of geometric configuration. But for definiteness, because I want to define some conformal maps, I'm going to assume this. And now, so one map I already know is the one that I call GT, which is uniformizing this curve. So I should have here gamma t. And I'm going to, let me call WT this square root kappa times BT for simplicity. So I'm unzipping this curve here, and then this blob is going to be somehow changed. It becomes some AT, right? Which is GT of A. So I can follow the evolution, but I could also first remove this A. I had some notation for that. Is that, and then the A is getting somehow collapsed, and the curve is getting transformed. This is the tip. So this is like gamma tilde t, which is, let's see, phi A gamma t. And after that, I could do a similar thing. And this would be some G tilde t map. And then again, the red thing goes somewhere to some W tilde t, which is, no longer the same. And okay, this is still there. And I decided how to normalize these maps. I'm hiding it here, but you can decide so that they look like the identity at the infinity point. If you do that, these are all uniquely determined. And you find here also a map which is collapsing this AT to this kind of part of the boundary and sending the WT to the W tilde T. And I would call this map phi AT. So there's the dynamics of these maps. And the diagram of maps commute if you normalize them correctly.
Sorry, how is the top left well defined? I mean, if the one with AT, it seems very wobbly somehow. I mean, the AT can be arbitrary, and the WT, like there's too much freedom, no?
So this is just the conform map from the upper half plane minus AT back to the upper half plane.
Yeah, my question is, how do you choose AT? It seems many different choices.
Equals the image of A under this GT map.
But then the question becomes, what is GT? Like how do you...
Okay.
You ignore A, define GT as a uniformization without A, and then put A back?
So input is that gamma is this SLE curve in the half plane now. SLE kappa. That I know it's a random curve like that.
Okay.
And well, I have input which is A. And to this one, I have associated evolution GT. So this is from H minus this H. Given. It was maybe a bit quick. This is from this Lerner's.
Yeah, what I missed is GT doesn't care about A whatsoever. I mean, GT is defined without...
Yeah, GT is... maybe it's not so obvious. Yeah, so GT is defined everywhere except here.
Okay.
It's the usual... it was kind of the thing that's here. We're getting A, but then A is going to move somewhere. Yeah. So maybe... the domain of... boundary of domain of definition... GT is like that, and then it's collapsing, there, and this blob is just moving. While here, I'm maybe running out of colors, so this is collapsing A and keeping this one. So this is gonna go from H minus A to H. So either you collapse the curve or you collapse the blob. So if you collapse the curve, you go this way. And this is all this stuff that you already know. or you collapse the A, you go here. And then after that you collapse the image of the curve, which is the tilde G, and then you end up having nothing. Or you can go this way, where this one is collapsing the AT. So I haven't written all the information, but I think the picture hopefully helps. So upshot, this one is conformal map chosen in a certain way. This one, well, similarly. So somehow it doesn't care about the curve. And then this GT and the G tilde T are this kind of learner. So G tilde T is killing the gamma tilde T. And GT we already know. But now here gamma tilde actually is image of gamma. So hope you can see from there. There's a little bit of parsing to do with this picture, but the point is that you can use this commuting diagram of somehow uniformizing either first the curve and then this A, or first A and then the curve, and you should arrive to the same kind of situation. You can use this to compare somehow the measure of the curve originally in the big domain and the measure in the smaller domain. So there's a lot of computation to do here to make it precise. But so what you get from here so from commuting diagram of maps, let's say, or conformal maps, you get something which is comparison of the probability measure in, let me write half plane maybe, minus A, from 0 to infinity. Obviously, I'm going to write in this way what you do for Radon-Nikodym derivative. So here is kind of, in terms of measures, this is a measure, right? And the original one, so H 0 infinity, easily. There's always the kappa. So this is something, and I need to check exactly what, but you get it from this picture. So somehow the idea is that you can do a perturbation of the domain by taking out something. You can ask, how does the measure change? And it's measured by a Radon-Nikodym derivative between, this is the original measure, without anything, just the curve in the half plane from 0 to infinity, forgetting about that. Upstairs is the measure affected by that, right? It's called restriction because you somehow chop off something, so you restrict to smaller domain. And this is exactly what happens there, right? And so in the end of the day, you get some kind of expression. Maybe I can write it here. Maybe not completely off. Yeah. So first you need to say that your curve is not allowed to intersect A. So just put indicator function. It doesn't go there because it's supposed to, under this upstairs measure, is supposed to stay outside A. It's just a triviality. Then there's the weighting factor, which, if I wrote correctly, has the following form. So I will explain more soon. Let me write it for concreteness. So there's a term that you don't know yet. This is the Brownian loop measure. You can write it more concretely as well. So I will explain it after I erase some stuff. So this is the interaction of the curve with this A, set A kind of. I will tell you what it is. This is the central charge, C kappa, which has some formula. I have exponential of that. And then there's also, so remember this was the uniformizing map of the A. So derivative of that at the 2 points. So it may be a bit mysterious, but I'm trying to motivate something by this. I guess, yeah, in my setup it's like that. Absolute value H1 2 kappa, which is the catch conform weight, also depending on kappa. Okay, so I need to remove some stuff to tell you more about it. So the point is that there is some geometric quantity appearing in the change of measure, which is the interaction of the curve to this set A. And now if the set A was like this, then you recover kind of what you need to do there. And the C kappa gives the conformal anomaly related to this kind of model. So that's explicit. Remember, I can write it here. Maybe it's like, is it called? P kappa means. Maybe kappa minus 6. I always misremember the sign. Something like that. So this is between minus infinity and 1. And H, let's see. Modulo some sign is something like this.
It is the other sign.
Huh?
It is the other sign.
I think it's missing some sign, probably. Always like that. Yeah, for the H.
Yeah, C of kappa.
C.
6 minus kappa.
Okay.
Ah.
And how about that? I don't know. It's one or the other. So this is supposed to be catch weight at level 2. And it so happens from computation that you see it here. But I guess it has a more deep meaning, which is somehow saying that there's some stuff happening at this starting and end points of the curve that's reminiscent of the CFT field it's out at level 2. Yeah. And this I haven't told you yet. So, okay. I will tell it in 2 ways. One is if you know what Brownian loop measure is. This is somehow, let's say, Brownian loop measure. Yeah. These would be half planes, or it doesn't matter because I can send it to other domains. So Brownian loop measure on the half plane. So if you don't know what it is, you can think about it as some infinite measure on loops that are living on the half plane with some geometric kind of property. So loops, let's say L, such that, I had to go here, L intersecting gamma is not 0, not empty, and L intersecting A is not empty. So you can assign some measure on loops built from Brownian motion. And you look at the measure of those ones that are touching your curve and this other thing. And here I need the curve really for all times, so I'm kind of drawing it all the way to infinity, and this is the A. Okay, so this is something, it's some infinite measure on loops built from Brownian motion. 2D Brownian motion. So this is very confusing if you haven't seen it before, but I hope the picture helps. So if this curve is really close to A, then there are many loops which are touching both because the distance is small. And then this measure is kind of bigger. If the curve is far away from A, not many loops somehow survive. If you think about this as two-dimensional Brownian motion started from somewhere, somehow efficient to come back to the same place, then you know it's going to go around, and normally they want to be quite small. So that's one way to describe it. So this is the interaction part.
Sorry.
Yeah?
What is the meaning of exponentiating this measure?
The exponential?
Yeah, because in the right side you have exponential of this central charge times the measure. I don't understand what is the meaning. The EXP term.
What's the easiest way to? So one way to see it, if you know what martingales are, is that change of measure is governed by some exponential martingale. So oftentimes you see this kind of thing. And downstairs is some normalization factor. It doesn't depend on the curve, right? It's just the derivatives of these conformal maps of this A set. If you don't know what martingales are, maybe one way to think about it is that there's some kind of, I don't know, Gibbs measure on loops, and this is some interaction part in such a Gibbs measure. And then there should be some action functional for this SLE. If this was some path integral type thing, which doesn't really make sense, but this would be maybe, path integral would be exponential of some action. And if you want to change the action, you put some more stuff in the exponential, which would be this inside here. I don't know if it helps at all.
So can this be written in terms of Icano, like an integral of Icano or something?
So you can write this one in terms of the determinant of Laplacian, at least heuristically. Determinant of Laplacian. But so for this fractal curves is not completely precise. So if you go to the semi-classical limit, everything is quite clear. Maybe I can explain it later. But there's one way to view it in this setup. You can also write it in terms of the Schwarzian derivative of this map, which is what you see in conformal anomaly. So I wanted to give you that formula. Because really that's the most. Right.
There must be an easy way of understanding that for kappa equals 2/6 that this that it doesn't even depend on this Brownian.
Oh yeah, exactly. So you can see that here there's the central charge. So if this is 0, there's nothing, right? But you still have to restrict. And okay, you have these factors there, but this
yeah,
just.
But that incidentally is also H12 is also 0, right? So
What is x12?
0, I think.
True. Yes. So yeah, there's nothing, but there's this part. It's just a sanity thing that you're not allowed to go outside of the domain. Yeah, so indeed, should make a comment here. So I was restricting to less than 4. So my case when the central charge vanishes is 1/3. Yeah, so C is 0 and H is 0. In that case, if I'm not mistaken.
No, H is not 0.
H is not 0 then. Yeah, sorry. C is 0. Okay, yes. So kappa equals 6 you can also do, but you need a little bit of more care, because the curve is actually almost surely going to hit this blob. And then when that happens, actually this one kind of blows up. But if the C is 0, it's not there. Yeah.
So I think in the paper of Roller, etc., they express this as the integral of the Schwarzian of some map.
Yeah, this is what I was about to write.
So, okay.
Yes. Because I thought maybe this is intuitive, kind of. But yeah, so this is, people say that 1/3 is the only case where you have a restriction property where there's kind of no interaction, because the downstairs is anyways a global factor. Never mind if the H is 0 or not, right?
So 1/3 is what? It's self-avoiding walk, or?
Yeah, this is a self-avoiding walk. And if you think about the discrete model for self-avoiding walk, which I don't want to go into, but if you know it, you can convince yourself easily that if you restrict to smaller domain, kind of nothing changes. And this is how you conjecture that the self-avoiding walk has to correspond to this kappa if there's a limit. We don't know that we cannot prove that the limit exists, but if it does, it has to be this one. And this was one point of this paper that they wrote to kind of try to identify that one. But then you can see that for other kappa, you need this kind of interaction factor.
Does this fundamentally change for kappa greater than 4?
So the problem is that this is going to hit A, so you need to condition on the event that is not hitting somehow, in some way, which is a probably 0 event. So, but fundamentally not. There's a kind of similar idea. Yeah. Okay, so what I want to say is that this loop measure also equals. Now there are some constants that I'm trying to keep track. It's -3, in case you're interested. No, 1/3. Right. Integral. I guess up to time infinity, because I have the whole thing, of the Schwarzian derivative of this phi map, evaluated at the driving point, dt. So what does it mean? It means that, so this is not clear from here, so you need to prove it, which is part of this paper. So it's the Schwarzian derivative of this map at this point. Somehow that's the effect, and you integrate over all times. I don't know if it helps much more, but that's at least some formula that you may be more familiar with. The Schwarzian derivative has a formula, right? And these maps are very, at least concrete. Yeah, and then there are some funny factors coming up that match nicely. But one way to think is that, yeah, here is some conformal anomaly related to like perturbation of the domain. And you can use this idea to do this interaction. So probably the interaction I can erase. Because you see the idea, I think. And then if you want more curves, you have to do it in some, either iteratively or with more care. And by the way, the way to prove it is using a martingale. So you can go, this paper is quite nicely written, but I think you need to know what martingales are. So you look at the martingale, which is the probability of this one not hitting A. And then you do a conditional expected value upon exploring, kind of. That's the usual strategy. But never mind much. Here is some geometric statement. If you believe it, maybe it gives some insight. So somehow upshot is that interaction of SLE curves should also be encoded in this way. Somehow via this conformal restriction property.
Oh, just one question. So if I pull back this integral by GT, do I get some, at least formally, an integral on the curve? Could you represent this anomaly as some integral on the, some contour integral on the curve? That would make sense.
Yeah, I guess short answer is that I haven't thought about it. But it's a good question. But it really also needs the information about this other set, right?
Mm-hmm.
Yeah. But so then you can do yeah. So maybe we can think about it later.
Some integral on the curve of the Schwarzschild phi x.
Yeah, exactly. Yeah, like that one. So in principle, it's yeah. So you need somehow.
We need to integrate with respect to some natural parameterization, I guess. Or
Yeah, something like this. Yeah, so here I've chosen the capacity parameterization, which I was kind of hiding, but it's from the explicit formulas. So yeah, if you change the parameterization, maybe you see something, some effect there. But let's see, so I wanted to quickly describe what this interaction has to do with CFT correlation functions. So maybe I'll go there in the remaining time. I'm happy to discuss later. So you can define these several curves which have the resampling property. Which was that if I explore first some of them, then the remaining ones are just the objects in the smaller domain. So you can construct it as follows. So you can take, let's see, so let me now decide how they connect. And maybe I want a little bit more points. Oops. So let's fix connection, fix connectivity, which is pairing of the points. So let's say somehow I want to call all of them x now for the sake of the exposition. x1, x2, x3, and so on. x2n. So I need even number of points for planar reasons, right? And then I want to say that, like, let's say xai connects with xbi, where this ai, bi are pairings of the points. A, N, B, N. So capital N is the number of curves that I'm going to have.
But if you alternated the labeling as x, y, x, y, x, y, and x would always connect to a y anyway.
Yeah, true. But I want to talk about correlation function with these points. So it's just a matter of notation. Yeah, I'm sorry about it. I'm used to it. So the point is then that maybe this one is connected with that. So this would be xa1, xb1, then this one there, and this one there. And if you believe me that if I know all of this, then I can construct all the different options as some convex combination. It's just much easier to discuss if I fixed one. And so the point is that to construct this kind of interacting measure, I could try to do just take the independent measures for each one that I already know, and then put interaction there. It's kind of a bit like what I was doing here. I have the independent thing, which is here downstairs, without any A, and then I put the interaction of the curve with A, and I get the upstairs measure. But now A is going to be these other curves. So you can, I'm writing the same kind of notation somehow. So downstairs is going to be in the big there's always this domain, right? X, AI. It's just endpoints of one, the ith curve, okay? SLE kappa. How to do it? Maybe like D. And then some product over these curves. This is just the product measure of all of the independent ones. And then my wanted measure should be somehow n SLE kappa, and it depends on this, often called this Aalto, because it depends on the choice a priori, kind of. And then it depends on moduli. Now there's more. There's D and all of these points, right? And alpha is kind of also part of the moduli. So what is this? Again, I need the indicator function that they don't cross, because that's natural for my discrete models side, and then times an exponential interaction part, which is very similar to there. So there's C over kappa times the loop kind of term in D. Let me write like that. Gamma vector is the couple of them. Gamma 1, gamma n, right? Gamma 1, gamma 2, gamma 3. So this is now a collection of random curves with interaction. Interaction is some loop expression that is kind of a generalization of that one. It's all in the exponential. Central or anomaly, unless kappa is 8/3, when kappa is less than 4, and we're just imposing that they don't cross. And now you may notice that this resulting measure is not a probability measure yet. So there's this normalization stuff that I kind of omitted. So maybe I should put some hat here, because this is a measure with mass, total mass, something else than 1. Okay? If I want to get probability measure, I need to divide by the total mass. It's a bit complicated with the notation, but I think the idea is very intuitive, right? And please say if I'm writing something wrong, because maybe I forgot some formula. So this M, in general, if you have many curves, this would be like a Brownian loop measure in your domain of loops. How to say? Maybe intersecting at least 2 curves. You can write in terms of some inclusion-exclusion thing, and hopefully I didn't write it wrong, but the idea is to generalize. So if you have 2, then it's as before. If you have more, it's a bit more complicated. But what I wanted to say is that, okay, you can construct this object. You can prove, for example, that for the Ising model, if you have this alternating plus or minus boundary segments, more than 1, these paths that you see there, they converge to this thing with kappa equals 3. So it's a reasonably natural guy, in some sense. Right, so remember that what is this kind of supposed to be meaning for critical models is this alternating boundary condition, sampling your model inside and following the interfaces. But this interaction part, so on this side, it actually depends on all of these moduli. I was kind of omitting some of it. So this has some kind of CFT meaning. And maybe you can guess something from here, because you get this conformal weight from those computations. So my claim is that the total mass of this measure is essentially given by a correlation function of some CFT fields which are degenerate at level 2. So I don't know how to construct these fields as a path integral or anything like that, at least yet. But I know how to construct the correlation functions. And these are boundary correlation functions because the points are on the boundary, right? But you could also think about boundary correlation functions if you move the points in the bulk as chiral bulk correlation functions of some fields. So it's somehow not that constrained as you would think. So let me just try to say some things about this. So I could define, I want to define in this way, because so there's all this moduli data, right? And the definition will be, let's see. So this is just the expected value for the downstairs measure, like independent, NSLEs, whatever, of your indicator function. So whatever is in the right hand side. And then e to the c over 2 of this loop measure part. So this gamma tuple is a random variable, right? So I can plug it in there, I get some quantity which is random. I can take expected value, so this thing is going to be a number depending on all this data. And then times, I need this kind of things. So it's a bit maybe of a nuisance to write it. But yeah. So this is meant to be a product of those kind of factors. So this one here is the Poisson excursion kernel between the 2 points, if you know what it is. If not, it's explicit for the half-plane case. So in H, the P, H, x, y is just 1 over x minus y squared. This relates to some tangential derivative of the green function at those points.
These are not random?
This is just a function of the domain and the points. So I fixed them.
Yeah, sure. I mean that in the normalization before you had something depending on A.
So that was motivational. Did I remove it? So A was some given set.
Yeah,
so
but now A is random.
Here is not completely obvious how it goes. Yeah. Yeah, so if you do this to some power, which is actually this. Did I do it correctly? We need to check. I was writing this formula in the note also. So you need this conformal weight. So what is the point is that you can actually prove that this is conformally invariant somehow. So you can send this MD is the same as somehow MH once you send everything. But these ones are conformally covariant. And the covariance is this kind of power. Maybe like of weight, this one. There's a lot of information here, but I'm trying to highlight the important bits. So one important bit is that there's this much more moduli, right? Because there's all these points. And a priori also this alpha, but it doesn't matter much, it's just the endpoints of the curves, right? And then here is the interaction part, which is maybe slightly mysterious, but if you believe me, you can make sense of it. And then this kind of covariance factor part, which maybe one explanation was that it appears somehow in there. And now I can regard this total mass, maybe times that part, so that's the total mass, and that's an additional part, but let me call it still total mass, as a function of the moduli data. And now can prove various things about it that kind of rigorously show that it's a correlation functions of determinate fields, in the sense that it satisfies a PD system whose solutions are uniquely classified. But what I don't know is how to realize it as some correlation functions of some actual random field.
Wait, sorry, I'm confused. So if you take n equals 2 in the formula that you just rubbed out? No, it's just below.
Here.
If you take n equals 2 and A is then the
The other one?
whole of, yeah. I mean, then I don't see how the two formulas are coherent.
I think I just wrapped up this, but the point was that this loop thing, did I write it wrong? So then here is just intersecting both. So it means intersecting the blob A and gamma. But in order to intersect the blob A, you have to intersect the boundary of A, which is the other curve.
Yeah, but then the normalization factor is random, so I don't. Then it depends on the realization of gamma, right? You had like the.
Yeah, so if you do it in that way, here I'm kind of doing all at once.
Okay, yeah, maybe I'm just confused with the. Okay, that's fine.
Yeah, so it's not completely clear from there, so you have to somehow prove this.
Okay.
With a separate argument. Yeah. So maybe it was more confusing than helping, but that's how the idea comes, that you can try to do it this way. And then it actually took a long time for us to figure out this, what is this term exactly. So, I don't know, for me it wasn't clear, even knowing this conformal restriction stuff. And it happens to work with this, this kind of stuff. So then just to wrap up, so let's say one can prove, because I don't have time to do that. And I should say there are many people worked on this in addition to myself, but you can find a lot of this in some of my papers as well, and then references. So what you can prove, that is Z, let me say, in our favorite domain, so that everything is more explicit, satisfies BPC equations with of level 2. So yes, I can write it if it's reminding someone of something. Modulus and minus signs that I always get wrong. So at each index j, you can have this kind of equation where the conformal weight appears. So each point has the same conformal weight in this model because each point has a curve attached to it. You generalize to some more complicated kind of interactions. So Z killed by that for all j. So for each variable, you actually have a degeneracy at level 2. And it's not obvious, probably, but you can prove also using a martingale argument that this has to be the case. They also satisfy this covariance property of primary fields. So I can write it in the way, you see it from here. So if I have, so now I'm working on the half plane, I guess just Möbius map, let's say. And I'm looking how this guy is changing. So the points are moving, fx1, fx2n. It's transformed by these kind of factors. So, and now I need to figure out how the powers go. So f prime at each point to power, what is it? Maybe h or minus h. There's always this h. Plus or minus. So that's immediate. Differential equation is not immediate, but it's somehow plausible from some stochastic calculus arguments. And this already is starting to look like, right? So then maybe look like this would be some correlation functions. So could imagine that this guy somehow, this is very heuristic, would be of this form, where this is a primary field at each point. Phi 1, 2. I'm hoping someone knows this notation. So if you take your CFT book, you look at the primary fields at degenerate at level 2, they will satisfy this kind of BPC equation, at least if you compute using translation invariance. They will have this kind of transformation property, modulo my minus sign mistakes. So it's plausible that they have something to do with each other. The funny part is that there's this alpha, that was the connection that I chose. There's actually more than one function. For each connection, there's a different function, right? So I've got some kind of linearly independent set of functions with these properties. And this is maybe a feature of the boundary. But you can show that these ones span solution space to this problem. So then if you have a CFT where this equation should hold, and you have some reasonable regularity assumption that I'm not writing here, which is very natural, you know that these functions give you, all possible solutions to this. So in particular, any correlation functions satisfying this has to be a function of these total masses, which is kind of, pretty cool, I think. Yeah. I'm probably supposed to stop very soon. So let me just mention without writing that I have these points on the boundary. I already mentioned that maybe you can put them in the bulk. Just put them here. So instead you can analytically just move the points because these functions are holomorphic, at least if the points don't collide. So you could look at them here. Maybe you could call them Z instead of X. And then this would correspond to some chiral bulk correlation function of these kind of degenerate fields, right? But there are still several of them indexed by this alpha guy. But now if you look at some Virasoro fusion rules that I didn't have time to discuss, there's kind of some labeling of certain Virasoro weights. So you can regard in some sense this guy as some kind of Virasoro block. But I think I shouldn't go too much over time because I forgot when we started. But I'm very happy to answer any questions you might have and explain more stuff. Yeah, thanks.